Good afternoon, everyone. My name is Dr. Helen Brindley, and I'm going to talk to you today about a new ESA Earth Explorer mission called FORUM, Far Infrared Outgoing Radiation Understanding and Monitoring Mission. And this is work that I'm presenting, but it's been done by a large team. I can't acknowledge them all in name, but they're all there in the FORUM team. So just to start off, I guess one question that you would like to ask is why should we bother observing the Earth's outgoing far infrared spectrum? So one motivation can be found by looking at this plot, which shows black body curves for different temperatures, just simulated out, ranging from the coldest recorded surface temperature that we see on the Earth to the hottest recorded surface temperature of the Earth, and also including the typical Earth's emitting temperature at the moment. And what you can see if you look at the plot is that the peak of the emission for all these temperatures actually occurs in the far infrared region, which we define here as wave numbers less than 667 inverse centimeters, or if you prefer working in wave length less than 15 microns. Now, that's just a black body curve, but if we look at theoretical simulations, we also see that the far infrared emission is really very sensitive to upper tropospheric, lower stratospheric water vapor, ice cloud and cirrus, possibly also potentially mixed phase ice and water cloud. And it also plays a dominant role in determining polar surface temperature and the polar energy, surface energy balance. However, no measurements of the Earth's outgoing infrared spectrum currently exist. It's very, very surprising. These measurements have been made for other planets, but not for the Earth. And theory suggests that 50% of the Earth's outgoing radiation actually occurs in this region. So it seems a really big gap in our understanding. And FORUM is going to fill this critical gap and give us these new observations that we need. So just briefly, I'm going to tell you a little bit about what the mission comprises. So the payload basically is two instruments. The main instrument is the FORUM sounding instrument, or the FSI. And this is an interferometer, or a spectrometer if you prefer, Fourier transform design, that is measuring the top of atmosphere spectrum across the infrared, actually from 100 to 1600 inverse centimeters. So covering the far infrared, but also moving into the mid-infrared as well. And you can see an example of the type of spectrum that we might not see from space in the plot on the left-hand side. Here in the red, you're seeing an example of what we might expect to see if a cirrus cloud is present in the spectrum, and in light blue, what we might expect to see for a clear sky scene just over the range of the FORUM measurements. The instrument will have a 15-kilometer footprint and less than 100 kilometer spatial sampling, and I'll talk a little bit more about this in the next slide. But really at its heart is the relatively high spectral resolution, so 0.5 inverse centimeters, and very, very high radiometric accuracy. So this is the sort of accuracy that we think we need to be able to see the climate relevant signatures that we're interested in the spectrum. So we're looking at an accuracy of 0.2 Kelvin or better for much of the range from 300 to 1300 inverse centimeters. And this is at 3 sigma, so this really hasn't been attempted before from space, and will be a challenge, but will be really exciting if we manage to achieve it. The precision of the measurements is not quite so important, but it's still pretty high and will hit in the main area that we're interested in around 0.4 milliwatts per meter square per steradian per inverse centimeter. And then to help us identify what's in the scene that we're looking at with the FSI, we will have an embedded imager, the FEI, and this is basically to try and identify scene homogeneity within the footprint of the FSI. So you can see in the plot on the right-hand side a example of what might be seen from both instruments in terms of their spatial sampling. You can see the FSI footprint in the circle and the FAI footprint in the square. And basically, you're looking to have a resolution of around 600 meters in the FEI, so that you can really pick up signatures of small cloud or changes in the surface conditions across the FSI footprint. Okay, so if we now move on to how we're actually observing with the instrument, We have the Forum satellite, obviously orbiting in sun-synchronous orbit in loose formation, actually, with METOP SGA-1. And this is in order to give us complementarity with IASI-NG, which is measuring the mid-infrared spectrum. So by putting the two instruments together, we will actually get the full outgoing infrared spectrum from space, spectrally resolved for the first time. And you can see that it's a stop and stare mechanism. So essentially the FSI stares at a scene for 14 seconds to gather the signal it needs. And then there is a gap of less than 100 kilometers, and then it stares at the scene again for another 15 seconds. And if you were watching the movie on the right-hand side, you'll have seen how the coverage of the Earth builds up in the top plot over a month. And in the bottom plot gives you an idea of the average revisit time for different locations on the Earth. So clearly we're going to get more samples near the poles up to the top sampling that we get, which is around 82 degrees north and south. And slightly reduced sampling as we move towards the equator. So that's a little bit about the mission. What I wanted to talk about now was a little bit about some of the observational studies that we've done in support of Forum at Imperial College. So we have built, several years ago now, the only instrument in the world that's able to measure in the far infrared from aircraft. It's called TAFTS. You can see its specifications on the slides here. And in concert with TAFTS, there's another instrument on the plane called ARES, which measures across the mid-infrared. So by putting the two together, again, we get full coverage of the infrared spectra from the aircraft. And we participated in a couple of campaigns, one in March 2015, which was out of Keflavik in Iceland. And we flew up over the Greenland Plateau, and that's the flight track you can see on the right-hand side of this plot. And then in the middle plot, in the middle at the bottom, you can see a second flight that took place last year, just off the North Sea, out of Stornoway, Scotland, to have a look at clear sky conditions over the ocean. And we have quite a lot of other instrumentation on the plane that helps you characterize the atmospheric state. We also regularly send dropsondes out of the base of the plane to measure the profiles of temperature and humidity below the plane. So I'm just going to focus, first of all, on the flights that we did over the North Sea in support of trying to find out a little bit more about tropospheric water vapor and what the far infrared could do for us there. So this is just a motivation for why we think the far infrared would be important. So here you're looking at simulated changes in the Earth's greenhouse effect. That's the difference between the surface emission and the top of atmospheric emission due to perturbations in atmospheric water vapor. And from top to bottom, you're looking at perturbations in the lower troposphere, the mid-troposphere, and the upper troposphere. And the amount of perturbation that you see there is actually sufficient to give the same perturbation as a doubling in CO2. So you don't need very much of a change in water vapor to actually have the same effect. But what you can also see is as you move from the lower troposphere to the upper troposphere, perturbing this water vapor, the signal becomes very much larger in the far infrared, mainly because of the change in temperature as you move towards the colder upper troposphere. So in our flights, we had a look at, first of all, forward modeling what we could see in the observed radiances. And that's what you can see in the right-hand plots at the bottom of the page. So first of all, you can see an example of the measured spectra from TAFTS and ARES. And in the bottom, what you can see is some attempts to actually simulate those spectra and the differences between the simulations and the observations. And we simulated them using a nearest forecast from the Met Office unified model, and that's what you can see in blue. And then we had an attempt to try and actually retrieve what the water vapor would be from the TAFTS measurements alone, from the ARES measurements alone, and from both of the measurements together. And that's what you can see actually in the green line. That's just using the combined retrieval. And you can see that the green line is moving closer towards the 0 line, which suggests that you're getting extra information from the measurements. And if you look at the plot on the left-hand side, what you're looking at is the actual humidity profile. You've got in black the profile measured by the dropsonde released from the plane at the time of the measurements. In blue, the profile from the Met Office forecast. and in green, the retrieve profile. And what you can see is that the measurements are definitely adding information in between the layer of 4 to 6 kilometers, and you're shifting towards the actual measured profile from the drops on. So there's definitely some advantage to having these radiance measurements. And what we see is actually that if we use the far infrared radiances alone without using information from the mid infrared, there's more information content for humidity in those measurements, and that's the first time it's been shown from observations. If we combine the far and mid infrared radiances, actually it doesn't have much effect on the quality of the humidity retrievals, but it does improve knowledge of the temperature and the surface temperature particularly. So again, you get more information content. And given the anticipated noise performance of FORUM, this suggests that the far infrared measurements really will demonstrate a similar benefit for characterizing the atmospheric state relative to using the mid-infrared only retrievals. So that's an interesting and important result. If we move on now to the second flight, this was the one that we were thinking about going over the Greenland Plateau. What we were trying to do here is have a look to see whether we could actually retrieve surface emissivity, not only in the mid-infrared, but also in the far infrared. So this is a measure of how emissive the surface is. The most emissive it could be would be a black body with an emissivity of 1, but most real surfaces have an emissivity that's slightly lower than that. But what's commonly been done in climate models in the far infrared is to say that the surface emissivity, particularly for any surface, is a black body. There hasn't been much account made for if there would be any variation in that. Some more recent work has actually suggested that if you put a more realistic representation of the far infrared emissivity in, and you can see some theoretical representations of what the emissivity would be in the left-hand top plot here, you have a very noticeable effect on surface temperature warming in the Arctic particularly, and that's what you can see in the top right plot. So you can see a very strong red colours suggest that by the 2030s, if you had a realistic surface emissivity in the far infrared in your model, you would get this much additional warming compared to considering it as a black body. And this also has been shown to reduce the bias in the modelled surface temperatures in at least 1 or 2 Earth system models. And this has been a problem in model intercomparisons for some time now. So what we wanted to do, we know that these theoretical estimates of far infrared surface emissivity might well then be important for Arctic and Antarctic surface warming, but there haven't been any real measurements of what the surface emissivity really is in the far infrared. It's a really difficult measurement to make. So what we did with our flights from Greenland was to actually go and see whether we could do this from aircraft. And we took measurements at high level, so from about 9 kilometers in the atmosphere, and constrained the atmospheric state, retrieved surface temperatures from the mid-infrared window radiances using an approach that was derived by Bob Knutson a few years ago, and then saw what we could do to estimate what the surface emissivity would be, making sure that we'd made a detailed analysis of the emissivity error budget. So what you can see in the top plot here is the assessment of what different contributions are to the retrieved emissivity error budget. And the things that you might expect to affect this are things like the surface elevation, how well do you know it, the water vapor spectroscopy, particularly the water vapor continuum, the water vapor profile, and also the temperature profile. And you can see in the different colors what the effects of various different things and perturbations are to the retrieved emissivity on the left in the far infrared and on the right in the mid-infrared. And then on the bottom, what you're seeing is the actual retrieved emissivities. And what you can see is cycle 8 is moving on the edge of the plateau. Cycle 10 is as you go up over the plateau, so you're getting to higher elevations. And you can see a distinct dip in the surface emissivity in the far infrared. So clearly it really is not one. And clearly there is some variability, and clearly you need to take this into account when you're thinking about particularly polar and Antarctic-Arctic energy balance. So our take-home message really is that you can do these retrievals, especially if there's a low water vapor column. As I said, the surface emissivity is significantly less than a black body. There are some caveats, so you do need to know what your surface temperature is or be able to retrieve it well, what the water vapor column is below your satellite, And also you need to be confident about your water vapor spectroscopy. So we think that actually we did this as a single target retrieval, but you could be doing a more optimal estimation type approach, which might mediate some of those issues. So I'm just going to finish off now with my final slide. So Forum will be Earth Explorer 9. I hope I've shown you that far infrared measurements will be beneficial for a number of applications. I haven't shown all of them, but there's just a couple of examples. So the overarching research objective will be to look for the first time at the role of the far infrared in shaping our current climate, with the idea that we can reduce uncertainties in future climate predictions because of its strong role in determining the Earth's outgoing energy. And all of the things that we're going to do in red there should help us to achieve that goal. And just to point out that the anticipated launch at this stage is 2026. So there's a lot of work to be done to prepare for the mission, but we're also very excited to see when these observations actually become available to use. Thank you.
Thank you, Helen, for a great talk there. I'll just remind everybody to send their questions in using the little question and answers envelope, please. But first up, I have a question for you, which was someone would like to know, what have been your biggest challenges so far?
Oh, crikey. I think getting the mission selected is always the biggest challenge. So that was very interesting, trying to present the mission to the user selection meeting. And then I think technically, the biggest technical challenges are probably the design of the beam splitter that we're using. So it's a wedge diamond beam splitter, which is quite technically difficult to produce, and the detectors themselves.
So, and another question is, do you think the Forum will benefit from the Truths mission?
Yeah, it's an interesting question. So actually, rather serendipitously, I have a PhD student who's actually doing a topic to see how they can work with each other to better benchmark climate. So obviously it's a completely different region of the spectrum. For those who don't know, Truths is a shortwave mission, so it's looking at high spectral measurements with high absolute radiometric accuracy in the visible and near infrared. So in terms of cross calibration, obviously there's nothing there, but you should potentially by using both of them improve your knowledge of the both the outgoing long wave radiation and the reflected shortwave. Obviously piggybacking with IASI-NG as well to fill the gap between the two in terms of the long wave part of the spectrum. How many co-measurements you'll have of both of them is sort of open to question, partly because of Forum sampling, but also partly because the Truths orbit hasn't been fully confirmed yet. So it'll be an interesting question to look at, and we're thinking about it, particularly in terms of perhaps characterizing natural variability of the climate system.
Okay, and another one, you're using an image to tell you if you've got structure in the beam of the data coming from the spectrometer, but the picture you showed had an image taken only at one wavelength. So how are you going to distinguish between temperature and density variations?
Okay, so the imager is really there to identify scene heterogeneity. It's not intended to use that imager really for retrieval purposes. So there are other instruments on board with on the METOP satellite, such as METIMAGE, which have many more channels on them. And because we're flying in loose formation with those, we'll be able to use some of the information there to give us more detailed information about the scene underlying Forum. The actual measurements that are coming from Forum themselves, so the interferometer measurements, in principle, you'd be able to use them also to give you more information about what sort of cloud, what sort of scene you're looking at too. So it's really to inform us on, have we got a homogeneous scene? Possibly you could get a little bit of information about whether it is cloudy or clear, but that's about the level that you're going for there.
Okay, and one final one just quickly is, why do you think there's been such a big gap with these measurements not being taken for Earth observation when we're measuring them for some time for other planets?
Yeah, it's an interesting question, isn't it? I think it's the level of accuracy that we think we need. So to get to the accuracy that we want requires quite advanced detector technology and this idea of the beam splitter, and they've only recently been developed. So I think that's the answer to that question.
Okay, so thank you again for an excellent talk, Helen.